will tell us about commitments to quantum states. Thank you.
I have until 15. I have until 12:15.
Yeah.
How much time do they have?
How long? No, no longer.
Yeah, 45 minutes.
12:20. All right, hi everyone. My name is Fermi, and I'm excited to tell you about commitments to quantum states. This is joint work with Sam, Nathan, and Mark. All right, so the motivating question for this work is a very simple question. Is it possible to commit to quantum information? Yes. Sorry. One sec, this clicker isn't. All right, I guess I'll use this. All right, so what I mean, Zvika, is the simplest setting imaginable. I have a sender and a receiver. The sender is just thinking about some quantum state. I'm going to write it as a pure state throughout today, but really this can be an arbitrary quantum state. It can be maybe entangled with something else that she holds on to. And all she wants to do is place the state in the equivalent of a digital locked box and send that over to the receiver. And later she should have the option to open this commitment in such a way that the receiver can verify this opening and then open this locked box and recover the originally committed message. Okay, so you may want some security properties to go along with this. And two typical ones are hiding and binding. And so hiding would say that the commitment should hide the underlying message, the quantum state, from the receiver. And binding should say that the sender can only open to a unique message, right? That once you commit, you can't really change your mind to something else. Okay. As stated here, it seems like there's a pretty easy answer to this question. There's actually a very simple sort of folklore scheme. Actually, if you were at Zvika's talk this morning, this was actually on one of the slides implicitly, where basically you combine something called the quantum one-time pad with any commitment scheme that allows you to commit to classical messages. So this latter can be classically or quantumly instantiated. And so here's how it works. Let's say you're committing to a 1 qubit message, just for simplicity. The sender will sample 2 random classical bits, A and B, and it'll send a commitment to these 2 classical bits. That's going to be this capital C. And along with that, it sends this one-time padded version of the state psi. So X here is the poly bit flip operator. It maps 0 to 1, 1 to 0. Z is going to be the phase flip operator. So it does nothing to 0, identity on 0. And on 1, it'll give a -1 phase. And the fact we need to know here is that if you take any arbitrary quantum state and you apply random X and Z's to it, you get something called the maximally mixed state. So this is a density matrix that's independent of whatever state you started out with. So that's going to be the commitment, is just this one-time padded state together with the commitment to the underlying keys A and B. And later you decommit to A and B, right? And so the receiver will verify this in the natural way. It just checks the classical commitment or the commitment to AB. And then it can additionally just recover the original message. It can just undo the pad, right? So it can apply Z to the B, X to the A to this one-time padded state and recover psi. So functionality, I think, is pretty straightforward. And security also seems pretty obvious. So for hiding, I'm not going to formally write anything out, but the intuition, I think, is pretty clear. You have 2 parts to your commitment. One part is this maximally mixed looking state, and the other part, maybe that causes trouble because it has information about A, B, but we know that the underlying commitment should be hiding. Okay, so this seems like a pretty easy hybrid argument. For binding, we want to say the sender can only open to unique state psi. It can't change the state after the commitment. And for this, well, I mean, the receiver is holding on to X to the A, Z to the B psi, so it holds on to that quantum part. And the only thing the sender gets to do when it opens the commitment is it can possibly change A and B. But that's precisely what the commitment to A, B prevents you from doing. So it seems like everything is just fine. There's one issue, which is that it's totally unclear what this actually means. Like, what do we mean mathematically when we say that a sender can only open to a unique state? And in fact, if you were to,
you said that psi could be entangled with something that that the sender controls.
Yeah.
Couldn't the sender then measure the other part?
Oh, and break security of this?
is, yeah, of binding.
I don't want to get into it, but it turns out you can't. Like you can, as long as the underlying commitment scheme is like post-quantum secure, you can't do things like that.
I think the point is that if he measures his state, the sort of the joint state of his own registers and the committed state changes. Like if if he has supers an X on an X and commits to X, like one of those X's, he can measure X, he can kind of technically change the state that's committed to.
I mean, in some sense, it's like all along you were just committing to the distribution of 0 and 1, right?
So by the way, can't I just say that there's an unbounded procedure using which the receiver can recover psi, and that is the only psi which the sender can open to?
You could say that. It wouldn't satisfy that property though. For instance, if it's not statistically binding, like this committed state could be independent of the receiver's view.
Yeah, but let's use statistically binding commitment C.
Yeah, you could do that for statistically binding. You could do something like that, I think. But let's aim for a definition that doesn't just work in that case. Okay, so just to sum up, our current understanding of commitments to quantum states is we have this one clean folklore construction, no security definitions. That's basically it. Nothing, yeah.
Okay, but Fermi, just to make the previous point, right? I mean, if it's statistically binding, then it's fine. Then you can make definitions and you can prove things.
You can, and nobody had done it, but I think you can do it. Nobody had written down even like a statistical binding definition for committing to quantum states. Not so hard to like think of one like as people are doing right now, but you will get very, very stuck in just statistical land.
Yeah, but the point is that you want something that's more general, right? There should be something that's more general.
Yeah. Yes.
You mean computational binding?
Yeah. But ideally, you want a definition of binding that's like not like that's agnostic to the attack model, right? You want some game where like if you just make the adversary unbounded, then you have statistical binding, right? You shouldn't have a definition that like only works in one, right? It's typically what we want like everywhere else in crypto. Okay. So the goal of this work is really to try to start building this theory of quantum state commitments. So contributions are in 3 parts: new definitions, constructions, and applications, and they all kind of go together. So on the definition side, our main contribution is a simple like game-based definition of binding. In one line, it says that when you commit to a state psi, that the state psi should be either computationally or statistically erased from the sender's view after you commit. So I'll say a lot more about what that actually means. So if it's confusing, like, don't worry just yet. This definition has a bunch of nice properties. It handles like, commitments to arbitrary entangled messages. That's going to be crucial for all the applications. It's falsifiable, composable, and parallel in sequence. It can be seen as a generalization of prior definitions for commitments to classical messages. And it has this cool property we call this hiding binding duality. And I'll get into that in a little bit too. On the construction side, we've already seen the construction of a hiding and binding commitment to quantum states. And indeed, like you can show this really satisfies this definition. And we also give a brand new construction. We give the very first succinct commitment to quantum states. So this allows you to take a long quantum state like n qubits and send a much smaller number of qubits to commit to this commit to this longer state. And both of these are going to be like completely non-interactive schemes. The commitment is one message, the opening is one message, and they rely on these like, weaker than one-way function assumptions. Like both of them are from assumptions that have been black box separated from one-way functions. Although the hiding binding QSC is from like potentially weaker assumptions than the succinct one. So on the application side, we have a bunch of applications in the paper. Really, the flagship application, though, is this use of succinct quantum state commitments to get a quantum analog of classical succinct arguments. So we have this protocol that is basically a quantum generalization of Kilian's classical protocol, where you can take any quantum PCP. So I'm just taking quantum PCP to mean some long quantum state, long quantum proof that you can check by just looking at a few qubits. And you can take any quantum PCP and compile it together with any succinct quantum state commitment, and you get a quantum communication succinct argument system. And so one thing this buys you is a protocol for much weaker assumptions than you know how to do classically. So we get if you instantiate the quantum PCP with a classical PCP, you get a 3-message succinct argument for all of NP from these weaker than only function assumptions. In comparison, Kilian's protocol takes one more message and uses CRHFs. Can be done from 3 with stronger assumptions.
No, but so your commitment, there's no kind of it's just really one message.
Yeah.
There's no kind of a hash.
Classical verifier.
Quantum, it has to receive qubits, and it has to. Everyone is going to be quantum in this world. Yes. Another thing you can do with quantum PCPs is hope that they're more powerful than classical PCPs. And indeed, this quantum PCP conjecture pans out, and we would have quantum PCPs for all of QMA. And in that world, this protocol would allow a richer set of languages than classical succinct arguments. And
you had this paper on post-quantum succinct arguments earlier, and now the difference is that your protocol also is quantum?
Yeah.
I see. And if the protocol is quantum, then were there constructions known earlier, or?
So there was the protocol that we analyze is like very similar to sort of Oracle model protocol that Lijia Chen and Rami Movasag had proposed like about a year earlier. And actually this project kind of started from looking at their paper and thinking about what it meant.
But what is known about this conjecture? Why is it?
I am not the right person to ask. All that matters here is that like quantum PCPs, like what languages we have quantum PCPs for? Well, at least NP, because I'm defining them to encapsulate classical PCPs. And maybe it goes all the way up to QMA, don't really know.
Is it possible to have like a commitment to a quantum state that is computationally hiding and computationally binding? I mean, because really, but the information has to be somewhere, right? I mean,
sorry, like, what do you mean? Like,
that it's not
statistically binding, it's also computationally binding. Right?
Yeah, no, I mean that it's not statistically hiding and it's not statistically binding. That's what I mean. I mean,
yeah,
both of them don't hold statistically, right?
I'm pretty sure you can have something.
You can?
I think you can have something where maybe like the X information's on one side and the Z information's on the other side, potentially. Yeah, like the folklore construction is just low and Z. Use different modes for the two.
Okay.
Right. Yeah.
Okay. Fine.
Yeah, and so for the applications, turns out to be like the most technical part of the work and the part of the paper that I'll get into the least today. But achieving all these results requires a bunch of new tools for rewinding quantum protocols and showing how to extract quantum states. Okay. So it's a rough plan for the next half hour. We're just going to go into this definition and explore this question of what does it actually mean to commit to a quantum state. Once we establish a definition, I'll talk about how to succinctly commit to quantum states, and then I'll briefly discuss what goes into getting quantum succinct arguments. All right, so actually before I go into this question, I just want to establish some basic syntax that I'm going to use for the rest of this talk. So we'll assume that the way that the sender and receiver commit to quantum states is by just applying some fixed like public unitary, or like fixed for every security parameter. So everybody knows the description of this unitary comp. And to commit, the sender is just going to apply this unitary to the message it wants to commit to, psi, together with lambda zeros. And what it's going to do is it's going to divide up the resulting state into two parts, the C part standing for the commitment and the D part standing for the decommitment or opening. And so useful sometimes to just call this joint state com psi. And so that's a state on C and D. And so you just send the C to commit, and then to decommit, you just send the rest of the state. Okay. So when you commit, you're sending a state that's going to be potentially entangled with the state that you're going to send when you open. And the receiver to verify is going to do the natural thing where it'll just collect these two parts together and then undo the commitment unitary, and then just check that the registers that are supposed to be 0 are actually 0. And if that check passes, then it's going to recover the committed state from the remaining registers.
You don't add classical. Can send also classical strings in addition.
So I will just treat classical as a subclass of quantum. So yeah, it can fit into this framework. And one more thing I'll add is that sort of any quantum state commitment can be rewritten in this form. So if you have a more general scheme with like rounds of interaction back and forth, there's a very fairly like elementary quantum transformation that's basically to like purify all the randomness of the interaction and kind of compress it into a single unitary. And then it's kind of based on some prior work by Junyan and the setting of committing the classical bits.
Is COM publicly known?
Is what?
Is COM publicly known?
Yes. Yeah, COM is publicly known. So both the sender and receiver have to know it to run their sides of the protocol. And that's all you write down to specify the scheme. Like there's nothing else I use to specify the construction other than this COM unitary.
It's random.
No, it's a fixed unitary for every lambda, for every security parameter, fixed in public description. Like any randomness that you need during the protocol will be like, generated from the quantum list. Like it will use those zeros to generate some randomness in units. Okay, any questions here? Okay, so now for this question, what does it actually mean to commit to a quantum state? And to kind of highlight the challenges that go into answering this question, I just want to recall the classical binding definition that we. So this definition says that a classical commitment scheme is binding if an adversary can't output a commitment state together with two valid openings to two different messages, so M0 and M1, where there's R0 and R1 denote the additional opening information. So you know. A bunch of things go wrong when you try to take this basic definitional template and extend it to our setting where you're trying to commit to quantum states. So let me just outline a few of the issues. So one issue is that in this definition, the challenger needs to verify that the two openings are actually valid. Right? It's to check that M0, R0 is a valid opening to C, and it goes and checks that M1, R1 is a valid opening to C as well. And in the quantum setting, when the commitments and the openings and everything are potentially quantum, this weird thing happens where maybe the order in which you check these two openings matters. Like what if when you check the first one, you like ruin the commitment, and then now you can't check the second one. So already you're running into issues like right away. Or maybe the more quantum phrasing of this is that the verification of the two openings might not commute. Also, when you have these quantum messages, there's other check that we never think about in the classical setting. It's totally trivial, just verifying these two strings are different. If those are two arbitrary quantum states that the challenger doesn't know in advance, then there's no like physical procedure even to verify that two quantum states are different. What does that even mean? And finally, a quantum attacker doesn't necessarily have to break binding in this way. Right? It doesn't have to, if it can change its mind about what it opens to, that doesn't necessarily mean that it can open to two different things at the same time. Like perhaps, it can open to either M0 or M1, but the way it opens to M1 is by destroying its opening to M0. And so this problem had actually been observed even in the post-quantum setting by several works. But kind of if you take all three of these things together, it's not totally obvious a priori that a good cryptography definition is possible when you're in the setting of just committing to information sort of from a continuous space. Okay, so as a result of all this stuff, our new definition is going to look a little bit different from this classical binding definition. So here it is. We call it swap binding, and here's a security game. So it's an interactive game between an adversary and a challenger, and the adversary is first going to send a commitment together with its opening D to the challenger. The challenger just goes ahead and verifies that C and D is valid, and if it's invalid, just stops there. It's not going to continue. And if the commitment is valid, then it's going to sample a random bit B. If the bit is 1, it's going to do nothing. It's going to leave everything alone. And if the bit is 0, it's going to replace the underlying committed message with a junk message. So what I mean by that is when I say swap psi with junk, what I mean is, well, first you have to undo the commitment to reveal the message. And then I'm going to run the swap circuit, which will just replace the psi with whatever other state I feed into it. So in this case, I'll just feed in the junk 0 state. So I replace that message with 0, and then I'll recommit. And then I send back this opening D back to the adversary. So the adversary's job in this game is to detect whether it got back its original opening or an opening to just a junk unrelated message. And we say it's binding if and only if it's hard to win this game, this distinguishing game, with better than 1/2 probability.
Are you also sent back or no?
I only send back this opening. So maybe a little bit more compactly and informally, what we're really saying is that commitments to psi should be indistinguishable for any side the adversary picks, should be indistinguishable from commitments to 0 if you only get to see the D part of the commitment. Right, so throughout this, we should think of the adversary as only getting to see the D part because we're thinking about you've sent the commitment away. Right, the only part you have left is D, the opening.
Yeah. One question. So why do you need to swap the state with junk? You can just say produce new
Yeah, you're totally right. We could, at least with this syntax, that's totally equivalent. I think in maybe a few more general settings, this definition generalizes a little better than that. But for certainly what's on the slide, you could imagine an alternative game where it's not a swap, but I just give you back a different opening. Yeah.
So wait, I am a little bit confused. So how does the state D which you are sending depend upon your bit B?
Oh, so if the bit is 1, then I just send back. So just assume the sender sends a valid commitment and opening, and then if the bit is 1, I always return the same D that it sent me. And if the bit is 0, I will send it back a decommitment to an unrelated message. So it has to tell whether it held on, whether I just gave it back the same thing, or whether I just gave it back some totally unrelated opening to a different message. So I think this definition is, on the face of it, a very weird way to define binding. Right? We typically think of binding as kind of a search problem, right, where you try to find some way to open the commitment in different ways. And for some reason, we've written down a distinguishing game here and said that binding is equivalent to succeeding in this distinguishability task. And so that, I think, requires a bit of justification. Yeah.
Should it be clear that this definition implies the former definition, or
no? No. Right. So the principle at the kind of heart of this definition is this thing called the swapping distinguishing equivalence, which is a sort of folklore in quantum information, but only recently formally written down in this work of Aronson, Atiyah, and succinct. And this says that the following tasks are equivalent for a pair of orthogonal pure states, x and y. And equivalent in a very strong sense. If you can do one with some epsilon advantage, you can also do the other one with epsilon squared advantage. And basically, the circuits you would use for either one are more or less the same with a few semantic changes. And the two tasks are swapping between the pair of states. So the task is given one of the states x, output the other state y, or y to x. And this distinguishing task where you're either randomly given x plus y or x minus y, and you have to tell which one is which. And there's sort of a proof by picture of this, where if you were to draw out what these states look like, you x and y at 90 degrees, and then you draw where x plus y is in the middle at 45 degrees, x minus y. Just to give some intuition, think about how you would show that a distinguisher gives you a way to swap between these states. So what would it mean to distinguish between x plus y and x minus y? Well, you might want to have a projection that can distinguish between these two. And where would this projector be? Well, claim that a useless distinguisher would be one that's right in the middle of the two states. Right? If this pi disk were right in the middle of x plus y and x minus y, it would not be able to distinguish between the two. They would have equal weights of measuring onto this pi disk.
Sorry, I missed something. So you're saying it's equivalent to tasks. One distinguish between the plus and minus, and the other is distinguishing between whether you swapped or you didn't swap?
No, the word swap is a little bit overloaded here, but what I mean is that change from one state to the other. So I give you the X state and you win if you can give me the Y state.
I see, okay.
So one is computational, one is decisional, right? That's the point. Swapping is computational.
Like one is more like search and one is decisional.
Yeah.
Yes.
Yeah.
Yes.
So one is the goal is given a state to produce an orthogonal state. I win.
Produce, well, in this setting, I fixed two states in advance. And they were in the AAS paper, they were concerned about like states that are very hard to describe.
Okay.
And they want to talk about like the concrete like circuit complexity of like implementing these tasks.
Great, thanks.
So that's not quite the crypto setting, but it's just the easiest one to just sort of describe this principle. If you have a distinguisher for these two states, x plus y and x minus y, the claim is that the distinguisher has to sort of be a little bit far away from x, right? If the distinguisher were exactly parallel to x, that would be like a useless distinguisher. It like perfectly can't distinguish x plus y and x minus y. But the moment you have the ability to implement a distinguisher that's a little bit away from x, that actually gives you a way to swap between the states x and y, the sort of proportional advantage. So one way you could do it, for instance, is just measure that pi dist. And then once you start with x, then measuring this pi dist gives you a state with some small component on y. And you can show this is like directly proportional to the original distinguishing advantage. And this really goes in both directions too, that if you have a way to swap, you can show it's really a reflection about a particular subspace, and like that subspace gives you a distinguishing measurement. Okay. So it's something that you can really like prove by just drawing this picture on a sheet of paper and really convincing yourself the tasks are the same thing. Okay, so let me try to translate that to the setting of commitments. And this is just to build intuition. So let's just suppose a sender honestly commits to a classical bit, so either 0 or 1. And so then we're looking at these computational tasks that involve a particular pair of pure states, right? So either this commitment to 0 or this commitment to 1 state. These are these bipartite states on C and D. And one thing we definitely want our commitment to satisfy is the sender cannot swap between these two states. That if the sender initially commits to 0 and then gives away the C part of the state, then by acting only on the D commitment part, it can't swap between commitments to 0 and commitments to 1. Right? That would be totally breaking the commitment binding security. And through this equivalence, it turns out that you can just write down the dual version of this task. Right? That what we want is that if we want to say that you can't swap between this pair of states, we could equivalently require that you cannot distinguish between the sum and their difference. And the sum of these two states is the commitment to the plus state, so 0 plus 1, and the difference is the commitment to the minus state, 0 minus 1. And it turns out that this is essentially like Unruh's collapse binding definition. So what Unruh has a paper defining this notion of what it means to be binding to classical bits and secure against quantum attacks. The definition is something about your inability to detect a measurement, and the fairly elementary quantum manipulations, you can show it's basically this requirement that you can't distinguish between commitments to plus and commitments to minus. So what we care about is, the setting where the sender may commit to arbitrary state psi. So just keeping things simple, let's suppose the sender honestly commits to some arbitrary pure state psi. And then we require that the sender can't swap between commitments to psi and commitments to some orthogonal state psi perp. Okay. And so the equivalent, the dual version of this task or the dual requirement is that we would say, well, they shouldn't be able to distinguish between commitments to psi plus psi perp and psi minus psi perp, given only the D part. And this is precisely what swap binding is going to guarantee us. That guarantees like for anything that you commit to. It's given just the D part, you can't distinguish that from the commitment to 0. So just one hybrid switch would give you this indistinguishability we want here. Right? Because both the left and right sides are indistinguishable from commitments to 0, given just the D part. So maybe that was a bit fast, but really like what we're doing with the swapping distinguishing duality is we're taking this thing we want to enforce, which is that the sender should not be able to equivocate between a commitment to psi and some psi perp. But we're the challenger, we don't know what psi is in the first place. Like we have no clue. The sender is arbitrarily picking this psi. So we don't really know like when it's changed from psi to psi perp. It doesn't feel like a a task that we can like efficiently where we can efficiently test if the adversary has actually done it. And what this duality lets you do is it turns it into something that is very easily testable, right? I can have the adversary give me like give me these states and then just play this distinguishing game where they're asked to decide whether or not I gave back their original state or their original decommitment or an unrelated one. And so that's really the role that this is playing. This basic quantum principle lets you take a task where it's not clear how you would test it and turn it into like a simple distinguishing game. And that's why it's possible to write down a cryptographic definition here. So I've only talked about honest senders here, but in the paper we really show that this swap binding definition captures security against arbitrary malicious sender strategies.
Do you show that these are in some sense morally equivalent, or is it just that you're doing it?
Which things are morally equivalent?
Like, is it true that if the sender can swap between and it can't swap between
it's infinitely, if I understand you correctly, it's infinitely. Okay, so a few additional properties this definition sort of mentioned already. It doesn't really care about whether you're committing to pure states or parts of some larger entangled state, and this is actually necessary for all the applications. And it's sort of readily composable. You can instantiate this in statistical or computational settings, and this allows you to formalize that folklore construction from earlier. So one other nice feature, was kind of surprising to us at least, is that this definition this swap binding notion is dual to hiding in a very precise sense. Maybe this was clear from the equivalence already, but and swap binding is saying that the D part of the overall like CD state hides the underlying committed message. And this whole time I've kind of swept hiding under the rug. I didn't even define it. But if you wanted to define hiding, the natural definition to write down, or a natural definition, would be the same one on the slide, except where the challenger sends the C register back to the sender, or to the receiver in this case. So hiding says that the commitment part, the C part, hides the underlying state. Okay. And so you get this nice way to sort of switch between your hiding and binding guarantees, where if you have a scheme where C is the commitment and D is the opening, you could imagine a dual scheme where you send the opening as the commitment and the commitment as the opening. And this like immediately swaps the computational or statistical properties of hiding and binding. So if you had a like statistically binding scheme originally, you would get a statistically hiding scheme after you swap the roles of the commitment and the opening.
So why is the binding at all? Like for example, thinking about the one-time pad scheme, that if you just send A and B, it doesn't bind you to the message.
Yeah. So it has to do with this like. That's a really good question. It has to do with this like general syntax that I've assumed, where that scheme is actually not written in that syntax. There's like this choice of randomness. And if you were to purify that randomness, you would get something where D is actually binding. If you were to get rid of all the classical randomness and write it as a single unitary, then you would actually get that D is binding. Okay, so
yeah. This previous slide says that there are two different schemes, one of which gives you hiding, one of which gives you binding. Don't we want to say that there's a single scheme that gives you both?
Oh, no, yeah. So if you start with a scheme that is both hiding and binding, then the hiding says that C hides the message, and the binding says that D hides the message. And so if you were to sort of switch the roles of C and D, you would still have the same thing. Both sides are individually on their own hiding the message. But if you had like a statistical guarantee on one side and a computational on the other, you would have switched them when you switch the roles of C and D. Yeah, you're totally right. You want it on both. You don't want it on just one, unless you have some other property. Right, so what I want to talk about next is how to succinctly commit to quantum states. And so what I mean by this is that I want to commit to an n-qubit quantum state with a commitment that's much shorter, so smaller than n qubits. And I just want this binding property. I'm actually going to forget about hiding. I won't actually need it for my applications. And with this duality, we can sort of reframe the problem. I mean, the dual scheme would be one where the opening is smaller than n qubits. And instead of binding, you have hiding now. And at least for me, like this is a little bit easier to think about. I think it's maybe more natural to think about like how do you hide information? We have many ways to do that. Because really the dual scheme is just a rephrasing of like, it's asking for an encryption scheme, right? It's asking for a way to encrypt an n-qubit message with a corresponding like opening register that is shorter than the message. And it turns out that you can do this whenever you have an encryption scheme where the keys, an encryption scheme for quantum states, where the keys are shorter than the state itself. And it's just one-time secure. So just a concrete example, so you can quantum one-time pad an n-qubit state with a pseudo-random string, and that'll work. So here's how this is an example construction. You could have a pseudo-random generator that stretches an n/2-bit seed to a 2n-bit output, and prepare a superposition over all seeds for this PRG. And then controlled on that seed k, you apply a pseudo-random polypad, the x to the first half of the PRG output, z to the second half of the PRG output. You apply that to this n-qubit state psi. Okay, so you've kind of like encrypted your state in superposition, and then you do this curious thing where you send away the keys as the commitment. Right, it's a very weird thing to do to like encrypt your own message and then send the keys to the receiver. But that's what binding says is the right. Like, that's what our binding definition says you should be doing. That binding security comes when the part that you hold on to as a sender hides your original message. So here, if I send away the keys, then from my point of view, if I only hold on to the D register, it looks like K is random. And once the seed for the PRG is random, then I can invoke PRG security to say that it looks like there's that the D register is just a maximally mixed state. This is like a true quantum one-time pad now. A few confused expressions, so maybe
It so doesn't work classically. It so doesn't work classically.
It really doesn't work classically. Yeah, you really like shouldn't do this. Yeah, it's like the magic of entanglement here is doing all the work. Yeah. Yeah. So yeah, because the seed to the PRG is short, this is a succinct commitment. And in fact, you don't even need one-way functions. So keeping in the theme with the workshop, in the paper we show that like this kind of encryption can be built from actually any so-called pseudo-random unitary. And by a work of William Kretschmer, this is like quantumly oracally separated from one-way functions, a potentially weaker assumption. So these succinct quantum state commitments in many ways behave like a quantum analog of collision-resistant hash functions. So they readily compose. You can take the moment you get 1 qubit of compression, you can compose that and get any amount of compression. And you can even do Merkle trees. So you can do a succinct commitment to a long quantum state and give short like local openings to individual qubits. And so this just looks exactly like a classical Merkle tree, except we've replaced every invocation of the hash function with a succinct quantum commitment. So you can start out with a long quantum state, break it up into small pieces, and then just tree hash this up with these succinct quantum commitments. And so classically, like these sort of tree commitments are the key cryptographic component of succinct arguments for NP. So succinct argument is a very, very efficient protocol, a very efficient interactive protocol between a prover and a verifier, where the total communication and verification efficiency is very, very good. It's much better than just extending an NP witness. And the argument part just means that we only ask for soundness against computationally bound provers. And in Kilian's protocol, in one line, the idea is you do a tree commitment to a locally checkable proof, or a PCP. And then after that, you do a PCP verification. Okay, so as I said earlier, we give a quantum analog of this protocol. So we show that with these quantum tree commitments plus any quantum PCP, you get a quantum succinct argument protocol. And it looks just like Kilian's protocol. So the prover will start out with its quantum PCP. It tree hashes it up using these succinct quantum state commitments and gets a short root of a few qubits, sends that over. And then the verifier will run a PCP check. So it'll ask to see a few positions of this quantum proof. The prover has to reveal those corresponding positions. So it does opens these like root to leaf paths. And this allows the verifier the verifier will check whether the opening is valid and then reveal the proof at those positions and run the PCP check. So maybe I'll skip the concrete corollaries and just jump straight to soundness. So the difficult part of this is not like writing down the protocol, but like thinking about how you actually prove that these protocols are sound, right? Under the assumption that you have a succinct QSC. So even in the classical setting, even when the protocol is entirely classical, this is not so straightforward. So let me just spend one slide kind of recapping what you do in the classical setting. So the way that you prove soundness of this interactive protocol is you do something called rewinding. So you say that if there is a prover that is sufficiently convincing, then I can run the prover many times on the last two messages and basically record its answers to many different random questions. And I store its answers across many questions in this extracted proof. And by the end, I either get some convincing PCP, some convincing proof that is as convincing as the prover itself, or I observe some inconsistency and find that the prover is breaking the underlying crypto. So already in the setting when you have quantum adversaries on the classical Kilian protocol, recording the prover's answers is not so straightforward because this recording can potentially disturb the prover's state. Right, so if you disturb the prover state, there's no guarantee it's going to answer you on your further queries. So this is something that we addressed in recent work with Alessandro Chiesa, myself, Nick Spooner, and Mark. But there is really a way, like even when the prover is quantum, to get this potentially disturbed prover state and to use it to answer later queries. So a one-slide recap of what this work is doing. Is that you're going to kind of run the classical rewinding template where you ask random questions to the prover, but now when it answers, you're gonna prepare its answers in superposition, and instead of just like measuring it right away, you're going to measure if the response is valid. So you compute this bit of whether the verifier would accept the prover's answer, and only if that answer is valid do you go ahead and measure the prover's response itself, the actual proof string. And then after that, all this measurement has potentially disturbed the prover's state, resulting in this new P prime state. And the hard technical part of CMSZ is coming up with this repair procedure, where you show that actually there is some way to kind of repair the prover so that it can answer you on further queries with the same success probability as before. And really the main idea of making this work comes from combining this statistical repair procedure with the guarantees of the underlying crypto, where you have to say that as long as the scheme is instantiated with a binding hash function, a collapse binding hash function, then the second step where you've measured the prover's response is undetectable. And then you can analyze this as if the step 2 didn't happen. And that's what really makes this repair work, that you can kind of bound the disturbance to the prover and show that you can repair the prover. So in our setting, this template doesn't quite go through, right? We need to extract a quantum proof. We're not trying to extract a classical proof string anymore. So at the very least, measuring the response isn't the right thing to do, right? That's not going to be enough to extract a quantum proof. But our definition kind of suggests what the natural quantum analog of this is when you're trying to extract the quantum proof. And that's just to swap out the quantum response into some external register. So, and the idea is to kind of run the same kind of template, but every time you get an accepting answer, swap out the quantum message. And the hope is eventually you get some good quantum PCP at the end. So when you get this accepting response, you run this swap, you record the answer in this extracted proof register, and then you repair or rewind. And the key point is that the swap binding notion says that this step is undetectable, that in the same way that measuring the prover's response is undetectable in the post-quantum setting, swapping out the message is undetectable when you're rewinding these quantum provers, these quantum protocols.
How does it apply cloning? If you can do that, how does it apply?
Next slide. Okay. 1 minute, you all. So this approach nearly works. except for what the talk basically said. But I'll phrase the problem a little differently, which is that there's kind of this tension between two different requirements you need on the extractor to make things work. And one key component of the way that the CMSC procedure repairs the prover state is it needs the extractor to be able to like run the prover and verify decommitments are valid. But at the same time, you need to argue that you can analyze the extractor as if it's only doing these 1-bit measurements where these swaps don't happen. And that requires you to appeal to the security of the underlying commitments. But like this whole talk, like you only have security if you give away the commitment itself, right? You can't have security if you're holding on to both the C and D parts of the overall committed state. So these requirements are totally incompatible for quantum commitments. Namely, like the first part, to verify decommitment, you need the commitment. And to argue any security, you need the extractor to not have the commitment. And so there's this very annoying tension between these two things. But really, like, I think what's been happening all along is that in the post-quantum setting, we could always get away with not worrying about the problem of verifying decommitments. Like, anyone can verify openings. And in the quantum setting, that's very far from true. This issue shows up even when you're just trying to extract classical information, as long as the commitment scheme is quantum. Basically in the paper, we show that there is some way to get around this by proving proving that swap binding generically implies a slightly stronger definition that gives you this limited access to the underlying message, basically giving you like a verification oracle. So maybe I'll end there and just say that for future directions, I think there's a lot of open questions that we've left. One thing, for instance, is can we build these succinct quantum state commitments from weaker assumptions, such as like pseudo-random states? Maybe could you remove quantum communication, or to what extent can you remove quantum communication from these protocols? And we definitely want like simpler techniques for rewinding and extracting these quantum protocols. Yeah, that would be a strong motivation for the second open question.
It's a very quick question. Yes. So just to clarify, we know them from PRUs, but not PRSs.
Yeah, we don't know them from PRSs. It's a funny thing where what you need is this like short key encryption of long messages, and we actually have that from PRSs in this AQI paper. And it doesn't work here, as Sam keeps pointing out to me, that because this AQI procedure is not unitary, it creates these junk states. And there's this problem of if you give the junk states to the sender or the receiver, if they give it to the receiver, it destroys the succinctness. If you give it to the sender, it destroys binding. And it's really unclear like how you do it. Yeah.
You need small key encryption that is.
Yes.
Okay, thanks a lot, Fermi, and we can take further questions offline. Final session of this workshop at 2 p.m.